Hi everyone, this is Dr. Saeeda Falafini. In this video, I want to talk about some of the basic concepts of queuing theory that we use in simulation modeling. So as we talked when we introduced the simulation, we said that simulation can be used as a tool for modeling service system and manufacturing. For example, we can model a bank, a call center, a supermarket, the traffic at the airport, or even a manufacturing process in a manufacturing plant. So let's see what are some of the common characteristics of this system. So if you consider a bank, for example, or a call center, some of the main questions or main challenges that the managers try to address is that how many customers are waiting in the line to get answered, because obviously they don't want to have too many customers waiting in the line. That affects their level of customer service. So the other thing is that how many agents have to have in the bank or in the call center so that they can provide a timely, relatively timely response to the customers, but at the same time they don't want to have too many agents, because in that scenario most of the agents may stay idle most of the day, and that's just extra cost and salary to the company, to the bank or to the call center, without really providing any benefit to the company. The same situation holds for a supermarket, for controlling the traffic that we may observe at the airports and so forth. So in all these systems, as you can see, there is a line, there is a queue of customers that try to get the service, and then there is a server or multiple servers, for example, the agents, the people who check out at the supermarket. So those are what we call as servers, and these are available, these servers are available to provide service to the customers. And the idea is to find the balance between in this system in terms of how many agents we want to have in our system and what is the level of customer service or timeliness of response we want to provide to our customers. Similar situation holds in a manufacturing plant. So in a manufacturing process, if you consider it, when parts come, they wait in the line to get processed in a machine. So and then when they get processed in the machine, they may leave the company or they may go to the next operation, to the next production process. In this situation as well, if there are too many parts waiting before a machine to get processed, that's always a question mark, a red alarm in the company that something is wrong. Why there are so many parts are waiting? So those parts pretty much are waiting in a queue to get processed at the machine. And then the question is that how many machines we have to have so that we don't have too many parts waiting in the company to get processed, because obviously those parts are potential revenue, potential profit, and that we can process as soon as possible and send it out. So in all these systems, we are dealing with the queue of customers or parts, and the idea is to have enough servers in the system so that we can provide reasonable service to these customers or parts. So all these systems are what we are examples of what we call as a queuing system. So queuing system, as you can see, is a setup, is a condition that is present in most of the system we are dealing with day to day, right, in the service industry or manufacturing industry. And the answer to the question of what is the right number of customers to have in the system, what is the right number of agents to have or right number of machines to have in the system is not something trivial that we can answer. So these questions can be answered in something that we call in a concept that we call queuing theory. So queuing theory is taught in operations research classes, and these queuing systems are basically the ones that we also want to analyze in a simulation. So in queuing theory concept, there are various mathematical models, there are various closed form formulations in terms of what is the right number of agents, what is the potential length of the line that we are going to see, and so forth. But queuing theory and the formulations have been developed for models with a specific level of complexity. But in the real world, we usually are facing situations that the level of complexity is high. And in those situations, queuing theory formula may not help us to answer these questions. In that scenario, simulation tools can help us to model those systems and then answer all those questions in terms of what is the right number of agents and so forth. So most of the models that we are going to basically analyze in the simulation are basically queuing systems, and we want to analyze them and answer the questions that the queuing theory cannot answer because the complexity of these models may be high. So again, if we go to the queuing systems in the service industry, one of the main questions that we want to answer is that on average, how many customers are waiting in the line in this system? Okay, answering that question can help, for example, to see what is the space we need to accommodate all those customers that are waiting. So that can help for example, the bank to think about the size of the bank or the size of the room in which the customers are going to wait. The other question is that how long these customers are going to wait in the line before they can get answered. And that's important to know for the managers because that affects the level of customer service, the level of customer satisfaction that they are going to meet. And so they want to make sure they meet the right level of customer satisfaction. The other question, for example, is that how many customers are in the system in total? When I say in the system, that means not only are waiting in the line, but also are with the agents getting answered or getting processed. So again, those are important questions in terms of seeing just what is the level of traffic in the system. And also lastly, what is the average time that it takes to answer a customer from the point that they enter the system till the point that they finally leave the system. So the time that the customer spends in the system in general, waiting in the line and getting answered by an agent. And again, this is the time that affects customer satisfaction. So we want to get a sense of how these metrics are in our system so that we can improve the performance of the system if they are not satisfactory. If you think about the manufacturing facility, we have the same set of questions. On average, how many parts are waiting in a line to get processed on a machine? So again, answering this question can help us to design the facility layout to see how much space we have to put before a machine so that we have enough space for all the parts that are waiting to get processed. On average, how long each part stays in the line before they get processed. And again, answering this question is important because we can find out if there are too many parts or if the parts are waiting too long to get processed. We may think of buying another machine or hiring another worker so that we can process these parts a lot faster. How many parts are in the system in general, and not only the parts that are waiting to get processed on a machine, but also the parts that are getting processed at each machine. So these are the parts that are basically are in the whole system. And again, that is important because those are pretty much a work in process for the company, and we don't want to have too many work in process because those are potential revenue. So we want to be able to send these parts, process and send them out as soon as possible so that we can gain revenue. And lastly, on average, how long does it take from the point that a part enters the system until the point that a part leaves the system? That includes the time that they are waiting in the line and the time that they are getting processed at the machine. So again, these are the times that we need to know because they affect our timeliness of response to our customer and affects our customer satisfaction. So these are typical actually questions that we answer in queuing theory. In queuing theory, when we analyze any queuing system, we have formulations for these type of questions that we can use to help the manager to design their system better. So if we look at on average how many parts or customer are waiting in the line, that's what we call as LQ, length of the queue. If we look at the question on average how long these parts stay in the queue, If we look at the question that on average how long these parts or customers are staying in the queue, are waiting in the queue, that's what we call as WQ, the waiting line in the waiting time in the queue. If you look at the question of how many parts or customers are in the system in general, not only the parts or customers that are waiting in the queue, but also the ones that are being processed, being answered, that's what we call as L, is the length of the queue in the whole system. And then if we try to answer that how long these customers or parts stay in the system in total, the time that they are answered and if you look at the time that these parts or customers are in the system in total, the time that they stay in the queue and the time that they are getting processed, that's what we call as W, the total waiting time. Okay, so these questions are answered in queuing theory with mathematical formulations for systems with a specific level of complexity, but we can also answer these questions in simulation models of queuing systems and capture any level of complexity that may exist. So that's the power of queuing system, that basically you are not limited in terms of the level of complexity that you are going to capture in your model. Okay, now that we have a better sense at what are the queuing systems and the fact that simulation is one of the tools that is going to help us to answer a lot of questions related to queuing system, let's see what are some of the inputs, some of the data that we need to have to be able to analyze these queuing systems and answer those questions. So when we want to develop the simulation model, or if we want to use even queuing theory to answer those type of questions that we just talked about, what type of data we have to provide to our analysts, what type of data we have to be able to answer those questions. So these are pretty much input to any problem related to queuing systems that we want to solve. Okay. So just one more time, this is a good representation of queuing systems. So there are, for example, arriving parts that arrive to the system. They are processed at the server, and then they leave the system. Okay, so this is just a schematic representation of the whole thing. Or this is another representation. The parts arrive, they get processed at server 1 or machine 1, and then they leave, they wait in the line for server 2 or machine 2, they get processed, and then they finally leave the system. So we can have any level of complexity. Just wanted to show you this so that if we show anything like this in our future systems that we are going to simulate, you know exactly what they represent. But what is important is that to be able to model this system, to be able to answer questions related to this system, as I said, in either simulation or queuing theory concept, we need two important input. The first important input to this system is arrival process, which is information related to frequency of the arrival of parts or customers to the system, how fast they come to the system to get processed. The other important input that we have to have is related to how fast we are processing these parts or customers and they leave our system. Okay, this is what we call service process, which is talking about how fast we provide service or we process these parts or customers and then they leave our system. Okay, so these are two important inputs we have to have related to any queuing system so we can process them and we can analyze them. So when you get any problem statement and you want to analyze the system using any method, simulation or queuing theory, you have to read the problem statement carefully and make sure you find information related to the arrival process and service process in the problem statement. You have to find information related to how fast these parts or customers come to the system, and also how fast these entities, these customers or parts are processed in the system and are leaving. Okay, so now let's see how these type of data or information is provided to us. For the arrival process, which is basically the information related to the frequency of the arrival of parts or customers to our system, we can get that information in two ways. One is in the form of arrival rate. So arrival rates are usually in the form of, for example, 10 customers per hour arrive to a bank, 20 parts per hour arrive to manufacturing plants to get processed, okay? So arrival rates always come in unit of time. So parts per unit of time, hour or minute or day or second. Customers per unit of time, again, hour, minutes, or any unit of time that you want to have. So when you have a unit of time in that measure that has been provided to you, that helps you to know that's in the form of arrival rate. So arrival rate always gives us units of customers or parts or anything in unit of time. Okay, and they usually are shown by Greek letter lambda in queuing theory. Okay, so that's one way, using arrival rate to basically provide that data to you. The other way is using interarrival time. What do we mean by interarrival time? That's the time between arrival of two consecutive customers. Okay, so for example, if we have 10 customers that are coming to a bank per hour, what is the time between arrival of two consecutive customers? Obviously, every hour has 60 minutes. If we get 10 customers in 60 minutes, that means that in every 6 minutes, one customer has arrived. So interarrival time, or the time between arrival of two consecutive customers, is 6 minutes. If we get 20 parts per hour in a manufacturing process, so given the fact that we have 60 minutes per hour, that means that there are 3 minutes between arrival of two consecutive parts in this manufacturing process. So the interarrival time is 3 minutes. Okay, so as you can see, if you have any one of this, if you have arrival rate, you can calculate interarrival time. And similarly, if I give you interarrival time, you can calculate arrival rate as well. So you can use them interchangeably. Okay. So if I tell you, for example, the time between arrival of two customers, or the interarrival time, is 15 minutes in supermarket, then you can easily calculate arrival rate of that supermarket, because 15 minutes of interarrival time means we will get 4 customers per hour in that supermarket. So as you can see, you can have any one of these metrics and you can calculate the other one easily. So, but as you know, these numbers are not fixed in any system. So, for example, it's not that in every bank we always get exactly 10 customers in each hour. So the average may be 10 customers per hour, but obviously in every hour this number may change. So right now we may get, for example, 8 customers per hour in this hour. Next hour we may get 12 customers. Next hour we may get 15 customers. Next hour we may get 5 customers. Okay, so what makes more sense is that we say the average of customers per hour that we receive is 10. However, these numbers can vary around 10. They can get larger sometimes, or they can get smaller sometimes. Okay, similarly for interarrival time, I may tell you that average of the time between arrival of two consecutive customers is 6 minutes, but this number is not fixed. So maybe the time between the arrival of the first customer and second customer is 6, and then there's between the second and third customer is 10, and then the time between the third customer and the fourth customer is 2 minutes. So this time between arrival of customers, consecutive customers, vary over time. So the better type of information that we can provide is that we say the average time between arrival of customers is 6 minutes, but it's not fixed. Obviously, it can get larger or smaller around the number 6. The average is 6, but it can vary obviously over time. Okay. In those scenarios, then you see the word average, the keyword average, next to the arrival rate or interarrival time. So when you read the problem statement, you have to look for the keyword average and see if, for example, I tell you interarrival time is 6 minutes or average interarrival time is 6 minutes. If you see the keyword average, that means the interarrival time is random. So when we have a random variable, we not only need to know the average of that random variable, but also we need a measure of variability around average, which is usually can be given by standard deviation or variance. But the best scenario is to have distribution of the random variable. So anytime you see the keyword average, the next thing you have to look for in the problem statement is the distribution of the random variable of the interarrival time, which is a random variable. So by having the distribution of the random variable, we pretty much have everything. We have a measure of the spread around the average of the random variable. Okay. The second set of information or data that you need to have to be able to solve a queuing system is related to the service process. Service process, if you remember, can tell us how fast customers or parts can get service and leave the system. The way this information can be provided to us is again in two ways. So one way is to provide service rate, and service rate again shows how many customers or parts can get service and leave in a unit of time, per hour, per minute, per seconds, per day, and so forth. So every time you see the service process is given to you as units of the customers or parts or anything per unit of time, that's service rate. And usually in queuing theory is shown by the Greek letter mu. The other way that we can provide this information is through service time. So service time shows the time that it takes to provide service to a customer or provide service to a part or process a part. So for example, if I tell you that in a bank, every agent can process 10 customers per hour, given the fact that an hour has 60 minutes, that means it takes 6 minutes to provide service to each customer. If I tell you in a manufacturing process, we have this machine works or processes 20 parts per hour, given the fact that each hour has 60 minutes, that means it takes 3 minutes to process each part in this machine. And that basically means that you can use service rate and service time interchangeably. I can give you service rate and you can calculate service time. And similarly, I can give you service time and you can calculate service rate. For example, if I tell you it takes 20 minutes to process a part on a machine, then I have given you service time, right? But then what is the service rate of that machine? Given the fact that every hour is 60 minutes and it takes 20 minutes to service one part, to process one part, then the service rate of that machine is 3 parts per hour. Okay, so you can use these two, service rate and service time, interchangeably. And similar to the arrival process, we know that in real world, the processing time or processing rate are not fixed number. For example, it's not that in a bank it takes exactly 6 minutes to provide service to a customer. Depending on what customers want, the time that the customers take are different from each other. What makes more sense is that you have average service rate or average service time. For example, on average in a bank, an agent can provide service to 10 customers per hour, but this number can change and can go higher or lower in different hours. And similarly, in a manufacturing process, on average, we take 3 minutes to process a part on a specific machine. But again, depending on the situation, the condition of the machine, and so forth, this time may go higher or lower. So we may take 5 minutes, for example, for the next part to process, or 2 minutes for the next part to process. So when you read the problem statement, then what you need to pay attention to is that if you see the keyword average. So if and not only for the service time, but also So what is important, and when you read the problem statement, is to look for the keyword average. If I have given you average service time is 6 minutes, that means average is 6 minutes. Service time is a random variable. Average is 6 minutes, but there are for sure some variability around average as well. Similarly for the service rate, if I give you average service rate is 20 parts per hour, that means on average is 20 parts per hour, but every hour we may process different number of parts, so there is some variability around the average. And similar to the arrival process, when we see the keyword average, that means, for example, service time is a random variable, and we not only want to know the average of this random variable, but also we want to have a measure of variability around average. And what can capture a measure of variability around average? Various factors, so standard deviation, variance, range, and things like that. But the best scenario is to have the distribution of that random variable. If we have the distribution of the random variable along with the mean and variance, then we know exactly how spread we are around the average. Now let's see how we can calculate interarrival time or arrival rate if we have only one of them. This formula shows the relation between interarrival time and arrival rate. So interarrival time is 1 over arrival rate, or arrival rate is 1 over interarrival time. Okay, so let's see how this formula works. Assume in a problem we have lambda or arrival rate as 10 customers per hour. So in a bank, for example, 10 customers per hour arrive to get service. We want to see what is interarrival time. So as the formula says, interarrival time is 1 over lambda. So interarrival time is 1 over 10. What is the unit of interarrival time? So if we put lambda at the denominator, we also have to inverse the unit of lambda. So then the unit of 1 over 10 will be hour over customer. Okay, so this is 1/10 of an hour per customer, which makes sense. But what is 1/10 of an hour, right? So we want to specify the interarrival time in minutes so that we can really understand them easily. So if I want to transform the 1/10 of an hour to minutes, all I need to do is to multiply 1 over 10 by 60 minutes per hour. And if I do that, the hours in the denominator here cancels with the hour in the numerator, and what is left is 6 minutes per customer. So the interarrival time is 1/10 of an hour per customer, or 6 minutes per customer. Similarly, for the service time, this is the case. So service time is 1 over mu, or service rate, or service rate is 1 over service time. So if in a manufacturing process, I tell you that the service rate of a machine is 6 parts per hour, what is the service time of that machine? The time that it takes to process each part. Service time is 1 over mu, or service rate is 1 over 6. What is the unit of 1 over 6? The inverse of the unit of the mu, hour over part. And so 1/6 of an hour per part. So if I want to transform 1/6 of an hour to minutes, so something that we can easily understand, then I have to multiply it by 60 minutes per hour. And again, the hours cancel each other. So what is left is 10 minutes per part. So service time of the machine is 1/6 of an hour per part, or 10 minutes per part.